pointed towards me. Around the blackboard. Which is what's more important. I've already hit start capture, so I should be on the video.
Yeah, exactly.
It's recording. You're okay, so. Okay, the lectures are now online. And here are the lecture notes. Thank you, Diane. So, http://w physics.edu video. Okay, so if I'm talking too fast, and you can stand listening to it again, then this is where you can hear it again. There are some notes, updated notes for the end of this chapter. We're just about to finish up. And the project, the term paper. So let me say a few words about that. So I'm giving you a list of possible topics in this handout. It's coming around, and it's very broad. If you don't like any of these topics, then you're welcome to find your own, but check with me. What I have here is, in this list, I list some idea for some topic for the theme of the paper. And then I give you a few clues as to where you might start in entering the literature. A few papers. Sometimes it's very sketchy. It's just the name of an author or something. You're supposed to be able to be grown up enough to go get onto the internet, go to the library, and find the relevant references. Sometimes I've actually taken the trouble to give you very precise references, but those are by no means the only references. You know, part of the game here is that you're supposed to dig into some topic and find out what people have been writing about it. Sometimes I have very, very standard topics. Sometimes I have things that are a little flaky. If it's flaky, you should come out and say, well, this is flaky. This doesn't make sense. Or be critical. Some topics are very straightforward. So if you want an easy time, you can just take one of these standard topics. I'm not telling you which ones are easy, but it should be. That you have to figure out for yourself. Some are very challenging. Some I would find challenging to work on, write an essay myself. I only expect something like 10 pages minimum. It's just supposed to be an expository paper, but, God bless you if you find it interesting and start thinking about it and start, come up with something original, then great. Absolutely great. So it's very open-ended. And I'm probably violating all sorts of rules, but you can hand it in just before Christmas, noon on December 22nd. But I'm not going to take anything after that. Okay, I read the papers over the Christmas break, and I'm certainly not going to be bothered with anything after that. So just forget it if you don't get it in on time. It's better to get in a half-finished paper than hand in nothing at all, because I won't accept anything later. All right. So last time we were talking about topology. Now, topology is relevant to instanton and soliton sectors. Now, later on in this course, I'll talk about an actual solution of the Euclidean Yang-Mills equations in 4 dimensions called the instanton. Here I'm using the word rather broadly. And so we were just talking about theories of scalar fields mapping from some space-time to some target space. And then to summarize what we said, if space-time S sub d is compact, then we can classify the space of fields that we integrate over in the path integral by a set of homotopy classes, because the set of maps, remember, maps from SD to Mn is topological space if you give it the compact open topology, and in that topology, the set of connected components, pi naught, is the same thing as the homotopy classes of SD into Mn. Now, if spacetime is non-compact, R sub d, then we had a finite action principle, which allowed us to compactify this point at infinity, and then the analogous statement is that we look at the homotopy classes of SD into Mn, which is pi sub d of Mn. And then there was a similar statement when space, not space-time, is compact. And then if we had a similar statement where we think about homotopy classes of maps of space into a target space. So if SD minus 1 is compact, then we look at these set of homotopy classes. And now instead of classifying the sum over components in a path integral, this would have to do with sectors in Hilbert space. So roughly speaking, this column here is about instantons in this broad sense. And this column here will be about solitons. And again, if space is non-compact, then we now have a finite energy condition, which tells us to look at SD minus 1 into Mn to classify soliton sectors. And then we looked at some examples. Now, I want to finish up this story by just saying a few words about spontaneously broken gauge theories, since the story is a little bit different there. Now, we're going to cover gauge theories in excruciating detail, but I assume that most of you have seen something about covariant derivative and a gauge connection, and you know how to think about it in terms of a locally defined one form. If you don't, then the next 4 pages are not going to make much sense to you, but I hope at the end of the course you can come back and it will make more sense to you. Okay, so what's the energy? So now I'm going to couple my scalars, let's call them phi, which go from SD into Mn, to gauge fields, supposing that theory of scalars has some symmetry group, some compact symmetry group G, symmetry group. Well, then the energy is going to look like something like an integral over space, some volume form, and then kinetic energy, where pi is the momentum, and potential energy for the derivatives of phi. Probably put in a spatial metric here, and some potential energy. All right. Now these are going to be 0 for static soliton, which is what we're interested in here. And now the covariant derivative, d alpha of phi mu, is the ordinary derivative plus our gauge field times some killing vector field acting on phi. Killing vector for this continuous symmetry group. Now, the set of classical vacua of this theory will be the set of phi such that u of phi is 0. So, as we saw before, and I'm going to just be considering, I should say, the theories on a non-compact space of type R to the d minus 1. And if G acts linearly, so that this killing vector field is linear, and phi is not 0, is a vacuum in here, then the symmetry is spontaneously broken. By the vacuum. Okay, now the finiteness of this energy implies that the limit as x goes to infinity of phi of x, phi of t in x, is going to be in this vacuum manifold. But what can happen in these gauge theories coupled to scalars is you can have d alpha phi mu goes to 0 at spatial infinity, but the limit as r goes to infinity of phi of t by mu of, let me just leave off the mu, that means just the whole component of Rx hat, let's call that phi infinity of t x hat, is well defined. And depends non-trivially on x hat. Now that's different from what we talked about last time, where the values of our scalar fields at infinity went to a constant. So because of that constant, we could compactify all of space, and that gave us effectively this map from SD minus 1 to M. Now what I'm saying is that when you have gauge fields coupled to scalars, you can have the values at infinity, the limit as the radius goes to infinity is well defined, but it actually gives you a function that depends on x hat. So then what we have here is instead a non-trivial map SD minus 2 into the space of classical vacua. Okay? Because the sphere at infinity, if you like the boundary at infinity of Rd minus 1, is the d minus 2 sphere. Okay, so we have this phi infinity here is defining a map from SD minus 2 into the classical vector. So the idea is that, how can this happen? Well, there are two terms in this covariant derivative here, and they can balance each other off. And so the total covariant derivative can go to 0 fast enough so that this term in the energy is finite. Okay, and then you would classify that in the solitons by pi d minus 2 of M classical vacuum. So let me indicate two examples of that. One is Mortises. So here we take a U1 gauge theory. Okay, and so I'll think of the gauge potential as some locally defined one form. And it has a field strength F, which is dA. And so then our action is going to be something like 1 over 2e squared of F star F plus d phi. I called it psi in the notes, but I really should have called it phi because that's what I used in the general discussion. Okay, it's a complex scalar field, so phi goes from our space, time, into just the complex numbers. Now, we can actually make sense of this in two dimensions, say 2 plus 0 Euclidean dimensions, or in 4 dimensions, 3 plus 1. And so if we're discussing, and so in this discussion I'm about to give, we should think of what we're talking about as instantons in 2 Euclidean dimensions, or vortex strings in 3 plus 1 dimensions. So the idea here is, imagine that this is an action in 3 plus 1 dimensions, but we now make the fields independent of time and some coordinate x3. So we have translation symmetry along the x3 axis. So then what we have is, here's the x3 axis, everything's time independent. There's a transverse plane to the x3 axis. That's the x1, x2 plane. And then all of the field dependence is in this plane. And so therefore, if we find an instanton in this plane, in the two-dimensional theory, you see, because everything is independent of x3, it's going to become a string-like object in 3 plus 1 dimensions. Is that clear? Is there any question about that? Okay? So simultaneously, we're talking about instantons in 2 Euclidean dimensions, or vortex strings, or string-like excitations in the 3 plus 1 dimensional gauge theory.
Excuse me. So you need some A non-trivial at infinity to balance that.
That is correct.
So that Yamir's part will also contribute some A.
That's correct, yes.
That would be finite?
Let's see. It will be, absolutely. But that reminds me that over here, I should have said plus a Yang-Mills energy. And I meant to correct that in the notes and forgot to. So let's correct that back in the beginning of the discussion. Plus Yang-Mills. Yeah.
When you say it's independent of x3, are we fixing a gauge on the?
Yeah. That's absolutely correct. I could, I mean, when I say it's independent of x3, I mean that we are going to choose a gauge in which it can be taken to be independent of x3. Absolutely. Okay. So, so now you see that the energy term wants phi squared to be equal to v squared. So this breaks u1 to what? Well, actually, I didn't tell you what the charge of phi is. So let's say it's charge q. And if it's charge q, continue that over here. Charge q implies that d phi is d little d phi, the ordinary exterior derivative, plus q a phi. Okay, so phi transforms like e to the I q theta, phi under gauge transformations by a goes to a plus I q u theta. Now that means that if phi has a vacuum expectation value, then I should, the unbroken gauge symmetry is the symmetry that leaves the vacuum value of phi invariant. And what would that be? Is EQ. Right. So in general, we break down to a non-trivial subgroup as EQ. So I'm going to take, we'll take Q equals 1 for simplicity, so our phi will completely break the gauge symmetry. But I should have said that this, of course, is an effective theory for superconductivity, where this phi here should be thought of as the wave function of a Cooper pair, in which case a Cooper pair has electric charge 2. And so in superconductivity, in fact, you break down the gauge symmetry down to a non-trivial Z2 group. Okay. But we'll take Q equals 1 here. And in any case, phi at infinity, at r equals infinity and theta, defines a map from the sphere at infinity into the set of phases, namely the set of phi. So this, you see, this is equal to v squared times e to the I some psi of theta. So this is a map from S1, the sphere at spatial infinity, to S1, the possible phases of our field phi, and that map can have a winding number. Okay, so that winding number measures the instanton number in the two-dimensional case, the string number in the four-dimensional case. And we can actually make this a little more explicit if we choose the special value lambda equals e squared over 2. Then we can write the energy. We can write the energy, which is, on the one hand, well, it's not quite the energy. I'll say in a moment what it is. It's the action in the two-dimensional case, or the string tension in the 3 plus 1 dimensional case, the energy per unit length. In either case, it's this, E3 squared plus D1 phi squared plus D2 phi squared plus E squared over 2 phi squared plus V squared squared. And then, similarly to our discussion of Landau-Ginzburg theory last time, we can rewrite this as the integral dx1 dx2 of 1 over 2e squared of v3, either minus or plus, both formulas are valid. Write a square there. We can also write a square here. This is plus or minus I d3 phi squared. But in writing the cross terms, we have made a little mistake, and we should correct that by adding 1/2 v squared of capital phi, where capital phi is the total flux. So capital phi is the integral dx1 dx2 of v3, and I should say that v3 is equal to IV3 is D1A2 minus D2A1 is F12. So in my conventions, A is locally a pure imaginary one form. That's so that my gauge covariant derivative is just D plus A. Okay, so now you see that the vortex, the action or the string tension is minimized by choosing the absolute value here and choosing the field configurations to satisfy these first-order differential equations. So we satisfy B3 equals plus or minus E squared phi squared minus v squared, and d1 phi plus or minus I d2 phi equals 0. And we choose the sign here so that this E is v squared over 2 times the absolute value of phi. So whether we choose the plus or minus sign depends on the sign of the total flux. So now you see that at infinity, phi squared goes to v squared. This was a v here before. But all we require here is that this goes to 0 at infinity, or actually for this minimum of the energy, it's 0 everywhere. But if you rewrite this, let's say with the minus sign, the second equation, so let's call this equation 1 and equation 2. Equation 2 can be rewritten as the statement that A sub z is equal to minus phi inverse dz phi, which makes perfectly good sense as long as phi is invertible, which we know it has to be out at infinity. And at infinity, this phi is just becoming a pure phase up to a constant v, which cancels out here. And so what this is saying is that the gauge field is becoming pure gauge out at infinity. And meanwhile, this phi out at infinity, as r goes to infinity, as a function of theta, is equal to v, as I said, e to the I psi of theta. And this mapping as a winding number, you see that this is equal to something like minus I dz phi of psi. And so if you now compute the flux here, by Stokes' theorem, that's going to be something like the integral of A out on the sphere at infinity. So if this has winding number W, this is going to be W. And so that's our topological quantum number. Okay, so that's how you can get these non-trivial strings in spontaneously broken U1 gauge theories. And the other example I want to mention, which is along the same lines, is the Intifada Cot Monocle. The discovery of this monopole was actually a pretty important event in the evolution of the interaction between physics and mathematics. And so, in the Intifada Cot Monocle, what we have is a gauge group, SO3, in 3 plus 1 dimensions. And phi is in the triplet representation. So it's a linear representation. And U of phi is g times phi squared minus m squared squared. So we have spontaneous breaking of gauge symmetry down to nothing. And the classical vacua, you see the set of zeros of this potential is the same thing as a two-sphere. And so now we have the two-sphere at, so phi infinity will give us the mapping of the two-sphere at infinity to the two-sphere, which is the classical vacua. And this map will have a winding number, an index, and that will be the monopole number. As we'll see later, when I discuss this solution. Now, in general, if we talk about 3 plus 1 dimensional Yang-Mills-Higgs, supposing that our target space for our scalar fields is some linear representation, V, and then U of phi is some invariant polynomial, so we then look at, to get the classical vacua, we look at the zeros of U of phi, classical vacua. And in general, if we choose some phi naught in this classical vacua, then the isotropy group will be some subgroup H, and that's the unbroken gauge symmetry. So then we're breaking the symmetry from G to H. And in this vacuum manifold, we have some phi naught, and then through the phi naught, there's going to be an orbit of phi naught. You see, if this is an invariant polynomial, then that means it's invariant under the G action. It's zeros are going to be invariant under the G action. And so through this phi naught, there's going to be a copy of G mod H. Now, in some good cases, like this example right here, we can actually have the classical vacua, the entire set of classical vacua, be a homogeneous space, G mod H. And then, when looking for monopoles, what we need to ask about is what's pi 2 of G mod H. So if you have some grand unified theory with grand unified gauge group G and some potential, which is breaking that grand unified gauge group down to some subgroup H, and you want to know, are there monopoles in this theory? Well, it's purely topological question. What you need to know is you need to know pi 2 of G mod H. And I'll be showing you in a couple of lectures how to calculate pi 2 of G mod H from something called the exact homotopy sequence of a fibration. So I hope that will give you some motivation to want to know that kind of homotopy group. Okay, so I think that finishes everything I wanted to say about this overview of why homotopy theory is relevant to instantons and solitons. I got a little out of order with some of the material by assuming in this discussion here that you knew a bit about gauge theories, but I hope you got the general picture of why homotopy groups are relevant. So now, if there are no more questions, we're going to start talking about principal bundles. So are there any questions? Okay. So now we go back to bundles. So cast your mind back to our chapter on bundle basics. So I remind you that a fiber bundle is something which is locally a product space, but has local trivializations where we see that the transition functions are simply things that glue fibers together by some action of a group on a fiber. Okay. So a principal bundle, I'm going to give two definitions, and let's call this definition A. A principal bundle, or a principal G bundle, is a fiber bundle. So P, pi, G, the structure group, E, the base, where the fiber is itself G, and the action of the structure group on the fiber is by left multiplication. That's all it is. So remember what that entails. So pi is a surjective continuous map from P to B. The fibers above X are isomorphic to G. And then on U alpha beta times G to U alpha beta times G, we have transition maps phi beta, phi alpha inverse, which takes xg goes to x, comma, g beta alpha of x times g. So the only difference from the general formulas we had before is that now the fiber coordinate is a group element in the structure group, and the transition maps are given just by left multiplication.
So E became P in this notation?
And E became P. That is correct, because P is for principal bundle. Yeah.
Oh, I
Okay, now.
see.
Yeah.
I'm sorry, I briefly got a chance to look at another book yesterday, and connected sum is the same thing as gluing.
Oh, well, you mean in the sense that I was just talking about gluing of fibers.
Oh, no, that's something.
Why did you, that's apropos of what? So,
Like to gluing to, like, connected sums of topological spaces.
well, okay, gluing is a term which could be used in many ways.
Okay.
So when I said gluing a few minutes ago, what I had in mind was that we have U alpha times G here, and then there's some subspace U alpha beta, and some U beta times G here, and some subspace U alpha beta. And now over here I have a fiber, over here I have a fiber, and I'm gluing a point G here to G beta alpha of X dot G over here. That's the sense in which I was using the word gluing.
Okay.
Somewhat
Something
imprecisely.
different, yeah.
Somewhat imprecisely. I hope this is precise for you. Okay. Now it's true that when you there's also a notion of gluing that involves connected sum of topological spaces. That's not what I'm doing here. Okay. Right, so we have a principal G bundle. And now an important point is that there's some extra structure here. So let's be a little clear about that. The point is that G admits both a left and a right action on itself. Okay? So remember, so R sub H, let R sub H be the map from G to G, which takes little g, goes to little g times H. That's a map from G to G. And it's a right action in the sense that if I take RH1 composed with RH2, I first do this, then I do that, that's equal to R of H2, H1. Okay, so that's a right action. Now, of course, there's also a left action by H, which takes G, goes to HG, and that is LH1, satisfies LH1, LH2, is LH1, H2. Notice the change of order there. Okay? So this is the rule for a left action, and this is the rule for a right action. Okay? And clearly, I can multiply on the left and right on a group, and so a group that admits both a left action and a right action. Now, in gluing fibers in this sense, what I have done is I have been using the left action. So now what we're going to do is we're going to use the right action of the group. So first of all, supposing I had a trivial bundle. So remember, every bundle is trivial locally, so this is always locally true. So I could define a right action on the trivial bundle by x comma gh. Now that is totally annoying. In your notes, does it say gh inverse? Equation 2.1. Yeah. Hope I'm not looking at the wrong set of notes here.
No, 3.1 is something else.
2.1.
2.1.
Ah, yes, yes, yes. Ah, the right section is correct. That's that question. I'm looking at the wrong set of notes. Okay. 2.3. 2.3 should be reading this, right? That is a right action on the trivial bundle E times G. Okay, are we all together? Okay. Yeah, so that's a right action. Now, for a non-trivial bundle, or a possibly non-trivial bundle, we have to use coordinate patches. And so we have this phi alpha from pi inverse of u alpha goes to u alpha times g. This homomorphism. So we have a right action here, and so we use the local coordinate patch to define a right action here. Okay, so we do that. So we define a right action here so that this diagram commutes. Okay, so that defines a right action, but then you can worry, well, what happens when we have overlapping patches? So our total space is up here, and there's some overlapping patches, and if I define the right action on pi, this space here, that's pi inverse of u alpha beta, if I define the right action using phi alpha, and then I define a right action using phi beta, do I actually get the same thing? And I'll let you work through the details, but the answer is yes, it's consistent. And so in local coordinates, what's going on is that here's our right action for a product bundle. And the gluing of fibers is given by a left action by this transition function, g alpha beta, in these coordinates. And you see, this diagram indeed commutes. So the vertical arrows are the gluing between the two coordinate systems. That gluing multiplies by the transition function on the left, you see. But the right action is defined on the right, and so those things don't interfere with each other. If I had tried to define a left action, I would have gotten into trouble, because then the h wouldn't commute with the g beta alpha of x. I would have definitely gotten into trouble. But because a group has both a left and a right action, there's this extra structure here of a right action which is globally defined. So that's the point. So there exists a globally defined right action R sub h from P to P, which moreover preserves fibers. Now, we also have local cross sections. We could define them to be S sub alpha of x equals phi alpha inverse of x1. So this S sub alpha of x is a map from u alpha to pi inverse of u alpha. And it's a cross section. It means that if I compose S sub alpha of x with pi, I get x. So these are properties we've derived for our principal bundle. And in fact, they give us a second definition of a principal bundle, which in many ways is more convenient. So a principal G bundle P is a space P with a smooth fixed point free right G action and a projection pi from p to the base, so that pi of p dot g equals pi of p. And there exist local cross-sections. Let's call them S sub alpha, which goes from U alpha to pi inverse of U alpha, so that phi alpha inverse from xg goes to S alpha of x dot g are local trivializations. Okay. So this is a second definition, and if you think through this, you can check that this is indeed equivalent to definition A. So the way you get the transition functions, g alpha beta, is if here is u alpha and here is u beta. So we have, by definition B, we have local cross-sections, so we could draw it like that. So above x, we have S alpha of x. And that's above this part here, which is pi inverse of u alpha. And then above this other part here, pi inverse of u beta. We have another local cross-section, S sub beta alpha. And so now we can compare these on the overlap here, pi inverse of u alpha beta. And the comparison is by a rotation by the right action of the group. So S alpha of x equals S beta of x dot G beta alpha of x for x in u alpha beta. And so now if you compare with the local, if you define local trivializations using your sections, then you can check that the overlap gluing here is indeed by G beta alpha on the x for the same G beta alpha of x. So I have an exercise in the notes that guides you through that, and I urge you to do that. Okay, let's talk about a very simple example. So let's look at principal Zn bundles over the circle. So the trivial bundle is easy. So that's just S1 times Zn. Now let's look at a non-trivial bundle. So let's identify S1 as the set of complex numbers of unit modulus, sitting inside the complex plane. And let's consider pi, which goes from S1 to S1, which takes a complex number z of unit modulus to z to the n. Well, z to the n, again, has unit modulus. So let's call that W. Okay. So what are the fibers like? What's pi inverse of W? Well, pi inverse of W is the set of nth roots of W. Okay? So now you see, if I choose one nth root of W, and I compare it to another nth root of w, then they'll differ by some phase, omega to the j, where omega is e to the 2 pi I over n. Okay. So this set here is the principal homogeneous space for Zn, which is the multiplicative group of nth roots of unity. That means that there's an action of this group on this set which is transitive and has no fixed points. There's no nth root that I can call 1. Okay? There's no nth root that I can canonically identify with the unit element of the group Zn. But it is true that Zn acts simply transitively on the set. So that means that what this map pi is describing for us is a principal Zn bundle of S1 over S1. Okay, what is the right action? The right action is just Z goes to Z times omega to the j. Everything's commuted, everything's abelian here, so it's also a left action, but conceptually, this is the right action I'm talking about. And pi of Z is pi of Z omega to the j, just like in my definition B. What about local cross-sections? Well, you see, when we choose a cross-section, what are we trying to do? We're trying, a cross-section is taking a complex number w and saying what its nth root is. Now, you all know that you can't do that consistently unless you choose a cut. So let's choose one cut. Let's call this u alpha and say that the argument of w is between pi minus pi and pi. And let's choose another cut and call that u beta and say that the argument of w is then between 0 and 2 pi. Okay, so on those spaces, those are contractible spaces, and I can make an unambiguous choice of nth root of w on those spaces. So we can define S alpha of w to be e to the I theta alpha over n. We can define S beta of w, where theta alpha is in that range, is equal to e to the I theta beta over n. W is equal to e to the I theta alpha equals e to the I theta beta. And what does u alpha beta look like? Well, u alpha beta, this example is a little funny and atypical in that u alpha beta is not connected. There's u alpha beta plus and u alpha beta minus. Now in u alpha beta plus, S alpha of w equals S beta of w. But on u alpha beta minus, S alpha of w equals S beta of w, right multiplication by e to the minus 2 pi I over n. So, right, because theta beta, which lies between 0 and 2 pi, has to be related to theta alpha, which lies between minus pi and pi. So theta beta minus 2 pi is theta alpha. So let's see if I got my signs right. Looks like I got it right. Okay. So you use that together with this, and you see that S alpha is related to S beta by right multiplication by e to the minus 2 pi I over n. Okay, so those are your local cross-sections. You see they're defined by this G alpha beta, and that's telling you how this Zn bundle of S over S1 is glued together, and the total space happens to be S1 again. So another way to look at this is a very important example to understand. So another way to look at this is that when we choose a cut, we're cutting open the circle to the interval, and so pi inverse of u alpha is the unit interval times, well, can be trivialized to the unit interval times Zn. And the elements of the fiber here are S alpha of W times omega to the J. So we have a copy of Zn here times the unit interval. But when we glue 0 to 1 with the unit interval, when we glue this fiber to this fiber, we're gluing them by left multiplication by omega to the J. Okay. Okay. Let me make a few remarks. That's the end of that example. Okay, remark 1. There's nothing sacred about left versus right. I could have defined my transition functions in terms of the right action, and then I would have a globally well-defined left action. Okay? So I will usually take my transition functions to be acting on the left on the fiber, and therefore a principal bundle will have a global right action, but not always. Now, another remark. So any space which has a smooth right fixed point free G action such that P mod G, the space of orbits, is a manifold. So if P mod G is a manifold and G acts on P without fixed points, then we have a principal G bundle. Now, you have to be careful about that because sometimes these quotient spaces can be very bad, non-Hausdorff, non-commutative manifolds. Okay? So I'll talk a little more about that later on. Now, another thing is that here, you see I can glue, in this example here, points in the fiber over 0 to points in the fiber over 1 by omega to the J. So that defines a whole set of principal Zn bundles. If I took J equals 0, you see I would get the trivial bundle, S1 times Zn. If I take J equals 1, I get the bundle I just described. But in fact, the isomorphism classes of principal Zn bundles over the circle is itself Zn. I have this choice here. Those are all inequivalent bundles. So there are many different inequivalent Zn bundles over the circle. Notice that they might have the same total space, but they're nevertheless in the different Zn bundles.
Excuse me.
Yeah.
So for higher J, you will get Z equals to Z. Jn? That projects.
No, that would define a principal Z. You mean something like Z to the nj? That would give me a principal ZNJ bundle.
Okay, sorry. Yeah, so how do you get higher?
Yeah, that's a good question. I was fretting about that on the way to class, to be honest. And I'm actually not sure. So you might want to take this and then divide out by Zn or something like that. That's a good question. So I actually don't know the answer to it.
So it's not the just the homogeneous function. I mean Z to the N.
Well, I can see from the gluing that there have to be these independent bundles. But yes, there has to be, and there is a projection. But I don't know how to describe them in terms of just the, nobody says it has to be of this form. This is just a particularly simple way to describe that bundle and its projection. Here I'm constructing a Zn bundle with different transition functions. Now nobody says it has to be like that. And I have to say I got confused about precisely that question this morning, but I didn't manage to straighten it out. Okay, so the last remark is the following. Supposing that I have two subgroups. Yeah, supposing I have H1, which is sitting as a subgroup of H2. And supposing I have a principal H1 bundle, like that, and then also a principal H2 bundle. Then I can make a fiber bundle. Myself some room. Then I can make a fiber bundle by projecting this to this. You see, this is equivalence classes under multiplying by, on the right, by H1. This is equivalence classes under multiplying on the right by H2. So there's an unambiguous map from this to this. If I've identified by H1 and I identify by more, that makes perfectly good sense. But then the fiber of this map is H2 mod H1. So in general, this is just a fiber bundle. But if H1 is a normal subgroup of H2, then it's a principal H2 mod H1 bundle. Okay. And we'll use that remark in a moment. Okay, so I reordered the material in the notes a little bit. So the next topic is not going to be the examples that are in the notes, but one more piece of general theory. And I guess they'll be in the notes next time. So I want to give now a criterion for triviality of a principal G bundle, PV, which is very, very useful. And so the theorem is that a principal bundle, now G bundle, it's very important that we're talking about a principal bundle, is trivializable if and only if it has a global continuous cross-section. Okay. So what's the proof of that? Okay, so first of all, if we have the trivial bundle, then it's totally obvious. Then we have a global cross-section, which we could just take to be x times the unit element. What's harder, of course, is suppose that S of x is a global cross-section. Now remember, local cross-sections always exist. But supposing I have a global cross-section S of x, So that means that pi of s of x is x, and then we have p down to the base by pi, and now we're making a right inverse of pi by this s. And the fibers here. So what can we do there to show that this is a trivializable bundle? That means I'm claiming that if this is true, then this bundle is isomorphic to the trivial bundle. So we define psi from b times g to p by taking psi of x and little g to equal s of x times the right action of g. So you see I'm given this global cross-section, and I'm going to define this map psi from the trivial bundle to my bundle p. Okay. So what do I have to show? I have to show that psi is a bundle map. So I defined what a bundle map was a few lectures ago. Right? I have to show that in local coordinates, it's a fiber-preserving map, which is left multiplication by some group element. Okay? Okay, now I have P, and suppose that the local trivializations of P are phi alpha goes from phi inverse of u alpha goes to u alpha times g. Okay? So therefore, phi alpha of s of x must be of the form x times, let's say, rho alpha of x, where rho alpha is a map from u alpha to g. So now let's look at the map u alpha times g, mapping by psi to pi inverse of u alpha, mapping by our local trivialization to u alpha times g. Okay, so you put together this definition and this definition, and you see that phi alpha of psi of xg is equal to x times x comma rho alpha of x times g. Now I'm using at this point the way I defined the right action of g before, okay? You have to go check that. So there's one little thing to check here. This uses the definition of the right action of g. Okay, but now you see that's exactly what we want. This is a fiber by fiber map. The x doesn't change. And on the fiber, g goes to rho alpha of x times g, and that's the left action of something on g. So that's just what we want. It's a fiber-preserving map. Now, at this point, it's pretty clear that it's invertible. I could have taken g inverse and so on. And so this is the isomorphism of bundles. And so that's the end of the proof. Okay, so a principal G bundle is trivializable if and only if it has a global continuous cross-section. Now let me make two remarks. First remark, it is crucial that we're talking about structure of fibers which are groups. Later on, we're going to talk about vector bundles. Vector bundles always have lots of sections, infinitely many sections, global sections. That doesn't mean that all vector bundles are trivial, far from it. Vector bundles can be non-trivial as vector bundles, but this is just the wrong criterion. I'm using very strongly here in this proof that the fiber is, that we're talking about principal bundles. The other remark, actually three remarks. Another remark is that if P is trivializable, notice the word trivializable, there might be many inequivalent trivializations. So you might be able to trivialize P with one bundle map to B times G, and another bundle map, psi tilde, to B times G. Okay? And psi and psi tilde might be different trivializations. Now you can always compose them, and so what you get is an automorphism of the trivial bundle with itself if you want to compare these two trivializations. And what is an automorphism of the principal bundle with itself? This psi tilde psi is simply a map from B to G. See, it's got to be of the form xg goes to x rho of x dot g. So automorphisms of these bundles have to look like this. So they're determined by a map from B to G. And so homotopy classes of B into G give inequivalent trivializations. Okay, that's remark 2. So a principal bundle can be trivialized, but in general can be trivialized in topologically different ways. Okay, remark 3. Now this is a remark, this is a common confusion, okay, which I want you to avoid. So every principal bundle has local cross-sections. In fact, that was even our definition B. Cross-sections. S alpha from U alpha to pi inverse of U alpha. And those cross-sections are related on the overlaps by S alpha of x dot G alpha beta of x equals S beta of x. Does that mean that there's a global section because I've glued the S alpha to the S beta by this transition function? Absolutely not. Okay? A global cross-section would require S alpha of x equals S beta of x for x in U alpha beta. It would require a single globally defined map. So you could say, what does this mean? What does this mean, excuse me? What does this mean in local coordinates? What it means in local coordinates, star, and I'll use that as an exercise, star means that on each U alpha, there exists a function, G alpha of x, from U alpha to G, so that G alpha of x is equal to G alpha beta of x times G beta of x. That's what having a global cross-section means. Now, it's so easy to get confused, right? This equation looks like this equation. But they're conceptually completely different. S alpha is a map from the base into the principal bundle. G alpha is a map from the local, from the U alpha into the group, the fixed group, okay, with its fixed identity. So here you're finding group-valued functions. Here there exist cross-sections. Very different. It's easy to get confused, but they're very different things conceptually. Okay. Now, one nice application of this theorem is another theorem. Okay, supposing I have pi, which takes P to B, is a principal G bundle, and B is diffeomorphic to a disk, the n-dimensional disk. Then the bundle is trivial. I could say trivializable, but you see, there are not going to be any interesting homotopy classes in that case. Okay. So, what's the proof? Well, by pullback, since B is diffeomorphic to the n-dimensional disk, I can just pull the bundle back to the disk. And remember that the pullback will be isomorphic. That P will be isomorphic to that pullback. So without loss of generality, we can think that P is a principal G bundle over the disk, the n-dimensional disk. So now let's take that disk and let's think of it as a radial coordinate times an angular coordinate. Okay, and so then we have a curve, gamma of r equals r times x hat. And so what we do is over the center of the disk, we just choose some g. And then we simply lift this path. Now I'm assuming something called the path lifting property, which I think is intuitively obvious in this case. We'll talk about that some more later. But we simply lift the path in any way we like, and we can lift for all the different angles. And so that gives us a global cross-section. So by our other theorem, this bundle is trivializable, and in fact trivial. Okay, so let me just take a few minutes to start the examples. So now I'm going to go through a bunch of examples, which are kind of fun. And we'll only get just a little bit started today. So the first thing I want to do is spheres covering projective spaces. Okay, so let's take Rn plus 1 minus the origin. Think of that as tuples of non-zero vectors, a1 through an plus 1. And there's an action on this of r star plus. Actually, I want all of r star. So the multiplicative group of non-zero real numbers. Okay, so if these are all non-zero, then that acts by taking this to lambda a1 through lambda an plus 1. And so the quotient space here is Rpn. Okay, so that means that we have a bundle r star over Rpn. Now another definition of Rpn is the following. We could take Sn, thought of as the unit sphere in Rn plus 1, and we could have Z2 acting on that, which takes x goes to minus x. And the quotient space there is, again, Rpn. And so Sn is a principal Z2 bundle over Rpn. So you see, Rpn is the space of these equivalence classes. Given by this multiplication here. Or, as we discussed briefly before, the moduli space of lines through the origin in Rn plus 1. And so every line goes through the sphere in 2 points, a point and its antipodal point. Okay, so I'm just quotienting out those 2 points there. Those are the, if you like, those are the 2 points in the fiber. So if you think of a point here in RPN as a line through the origin, that line pierces the sphere in 2 points, and those 2 points lie on the sphere, and that's the fiber. And so those 2 points are related by this Z2 action. Okay? So we had a principal Z2 bundle over RPN. Now, you might ask, how are these, before we ask that, let's ask one thing. Is this a trivial bundle? Or at least a trivializable one. So could it be that we can identify Sn with RPN times Z2? No? Why not?
Unless I'm interpreting it correctly, the right-hand side. In 2, at least for RPN 2, you can't cover it with a sphere.
Why not?
Because if you try to identify the opposite points, it's just like you try. It's hard to. It's not a sphere when you're.
Why not? Give me a proof. Might be hard, but maybe you're just not clever enough to find a way to choose a point.
So to get a loop from one pole to the other pole. And then,
Okay. Okay, so, yeah, so Omar's talking about this, it's kind of hard to draw RP2. Here we have S2 down to RP2, and here's the point. It's opposite. Yeah, and now what do you want to do?
I mean, it's a segment in S2, but it's not a loop in S2, but it's a loop in.
Okay, so you can take a loop down there, and I do agree that that will project to a closed loop down in RP2. It's true. It's a true fact. So what? Yeah. Not contractible to a point. Good. You're on the right track. That's not quite right, because neither side is contractible to a point.
It's not connected.
There we go. This is connected, and this is not. We don't need to know how many components RPN is. We know that there are at least 2 components because it's a direct product with Z2. So, but that way, it's kind of amazing. Okay, so it's locally disconnected over the patches. There are only 2 inverse image points. X and minus X. But the sphere is connected. So it can't possibly be a trivial bundle. Now, how are these 2 examples, how are these 2 ways of presenting RPN related? Well, you see, they're related exactly by my comment about H1 and H2. So if I take the positive invertible real numbers, then that's a normal subgroup of the invertible real numbers, and the quotient is Z2. Okay, so we have R plus star. That acts on Rn plus 1 minus the origin, and the quotient is the n sphere. That is a trivial bundle. But then we have H2 mod H1, which is Z2, over RPN. Now, it can often be the case that two ways of presenting quotient space can be useful because from one point of view, something might be obvious, which is not obvious from the other point of view. So, from this point of view, the quotient of the sphere mod Z2, it's completely obvious that RPN is a compact space. You have a compact group acting on it, a freely acting, compact discrete group freely acting on a compact sphere. Clearly the quotient is going to be compact. However, if I just told you this up here, from here it's not at all obvious that RPN is a compact space. I have some non-compact space and some non-compact group acting on it. Who knows? Maybe it's compact, maybe it isn't. It's not obvious from this point of view. Okay, so I think this is a good place to stop. I will begin next time with similar remarks about CPN and HPN, and then move on to some other examples of principal bundles.
You're booking my office. So if you're working, I can give it to you.
Okay, so you click finish.